Welcome students. Today we will learn the chapter of oscillations. Motion of a body can be classified into three types: translational motion, circular motion, and oscillatory motion. Translational motion is motion of a body along a straight line path or along a curved path. Examples of translational motion are many, right from crawling of an insect to motion of an aeroplane. Circular motion is motion of a body along the circumference of a circle. Motion of the earth round the sun, motion of the moon round the earth are the examples of circular motion. Oscillatory motion is a type of motion in which a body moves to and fro, tracing the same path again and again in equal intervals of time. For example, pendulum of a watch, needle of a sewing machine, etc. All these motions are periodic motion. In this type of motion, the particle performs the same set of motion in equal intervals of time. One such set of motion is called oscillation. In oscillatory motion, the force causing the motion changes in both magnitude as well as direction. Hence, it is called simple harmonic motion or SHM. If the object is moving along a straight line path, it is called linear simple harmonic motion or LSHM. In SHM, the force causing the motion is directly proportional to the displacement of the particle from the mean position and always directed opposite to it. Thus, if x is the displacement of the particle from the mean position and F is the force acting on it, then F is proportional to minus x. Here, the negative sign indicates that the direction of the force is opposite to that of the displacement. Hence, F is equal to minus kx, where k is a constant called force per unit displacement or force constant. The unit of k is Newton per meter in SI and dyne per centimeter in CGS. The dimensions of k are m1 L0 t raised to minus 2. It can be proved that SHM is projection of UCM on any diameter. The figure shows a particle P in UCM with center O and radius A. M is its projection on diameter AB. Let the particle starts its motion at t is equal to 0 from P0 such that angle DOP0 is equal to alpha. In time t, it moves from P0 to P1. Its angular velocity is omega. Hence, angle P0 OP is omega t. At this instant, its projection moves from O to M such that distance OM is x. In right angle triangle OMP1, sin omega t plus alpha is equal to x upon a. Therefore, x is equal to a sin omega t plus alpha. This is the equation of the displacement of the particle performing SHM from the mean position in terms of maximum displacement a, time t, and initial phase alpha. If we find time derivative of this displacement, we get velocity v as a omega cos omega t plus alpha. If we find time derivative of this velocity, we get acceleration. Hence, acceleration is minus a omega square sine omega t plus alpha. But a sine omega t plus alpha is x. So acceleration is equal to minus omega square x. The negative sign indicates that the acceleration is always opposite to the displacement. When the displacement is away from the mean position, the acceleration is towards the mean position and vice versa. Also, its magnitude is directly proportional to displacement. Hence, SHM is also defined as the type of linear periodic motion in which the force and the acceleration is always directed towards the mean position and is of the magnitude directly proportional to displacement of the particle from the mean position. From the formula for force, we can get also K upon m as omega square. The SHM can be described in terms of differential equation also. There are two differential equations of SHM. The first one is m d square x by dt square plus kx is equal to 0, where m is the mass of the particle performing the SHM, d square x by dt square is its acceleration, k is the force constant, and x is the displacement. Then, dividing both sides of the equation by m and substituting k upon m as omega square, we get one more differential equation as d square x by dt square plus omega square x is equal to 0. By solving these differential equations, we get two important formulae. One is for velocity, that is plus or minus omega under root a square minus x square, where omega is the angular velocity and a is the maximum displacement. Also, we get the same formula for displacement as x is equal to a sine omega t plus alpha. When the particle starts moving from the mean position, that is at t is equal to 0, x is also 0, we get the value of alpha as 0. When the particle starts from the extreme position, that is t is equal to 0 and x is equal to a, we get the value of alpha as pi by 2. Thus, when the body starts moving from extreme position, the initial phase of the body is 90 or pi by 2 radian. Now we will define different terms regarding SHM. First, very important and frequently used term is amplitude. The maximum displacement of the particle performing SHM from its mean position is called its amplitude. It is denoted by A and it is expressed in meter. Then, as the particle moves on both sides of the mean position O, the path length travelled by the particle is 2a. It is also expressed in meter or centimeter. Oscillation. One set of motion is called oscillation. In the figure, when the particle performs one oscillation, it moves from O to A, then A to B, and again from B to O. Then it is said to have complete one oscillation. Phase of SHM. Phase of the particle performing SHM is its state of oscillation or state of motion. In the equation x is equal to a sine omega t plus alpha, omega t plus alpha is the phase of SHM. In this, omega t is the present state or present phase or phase after time t, and alpha is the initial phase or the starting phase or the phase constant, or it is also known as epoch of SHM. Phase, omega t as well as alpha are measured in radian. Period of SHM. Time taken by a particle performing SHM to complete one oscillation is called periodic time or period of SHM. It is measured in second. The formula for period of SHM is given as T is equal to 2 pi by omega, or T is equal to 2 pi under root m upon k. Frequency of vibration is defined as the number of oscillations completed by the particle performing SHM in 1 second, that is unit time. It is measured in hertz. As frequency is reciprocal of period t, the formula for frequency is omega upon 2 pi, or it is 1 upon 2 pi under root k upon m. Along the oscillation or along the path of SHM, the velocity and acceleration doesn't remain constant. Velocity of the particle performing SHM is maximum at the mean position. This maximum velocity is a omega. When the particle reaches the extreme position, its velocity is 0. So minimum velocity is 0. Similarly, acceleration also does not remain constant. When the particle is at mean position, its acceleration is 0. And when the particle is at extreme position, its acceleration is maximum, given by the formula omega square a. Similar to velocity and acceleration, the energy of the particle performing SHM also changes as per the position. However, the total energy of the particle remains constant. When the particle is in the mean position, its velocity is maximum, so it possesses maximum kinetic energy. When it is at extreme position, it is maximum away from the mean position, hence it possesses maximum potential energy and minimum kinetic energy. However, the total energy remains constant. When the particle is at mean position, it possesses maximum velocity. Hence, its maximum kinetic energy is same as the total energy. Similarly, at extreme position, it possesses maximum potential energy. Hence, it is also equal to maximum energy possessed by the particle. The individual formulae for potential energy and kinetic energy are: potential energy is equal to 1/2 kx square, where k is the force constant. If you substitute k as m omega square, it will become half m omega square x square. The formula for kinetic energy is half m omega square into bracket a square minus x square. If you add these two energies at any instant, it will be half m omega square a square. Now in this formula for total energy, every term is constant, which proves that total energy of the body performing SHM is constant. When the body moves from mean position to extreme position, its kinetic energy decreases and potential energy increases by the same amount. However, the sum of these two energies remain constant. While coming back, that is from extreme position to mean position, its potential energy decreases and kinetic energy increases by the same amount. Once again, the sum of the energies, that is total energy, remains constant. The variation of potential energy and kinetic energy is described in the graph shown. A particle can be subjected to two or more SHMs at a time or simultaneously. These SHMs can have different paths, periods, amplitudes, and initial phase angles. The resultant displacement of the particle is vector sum of the displacements produced by the SHMs individually. This is called composition of SHM. The simplest composition is the composition of two SHMs having same period, that is omega t, same path but different amplitudes A1 and A2 and different initial phase angles alpha 1 and alpha 2. If x1 and x2 are the displacements produced by these SHMs in the particles at a time independently, then according to the equation of SHM, x1 is equal to a1 sin omega t plus alpha 1 and x2 is equal to a2 sin omega t plus alpha 2. The composition of these two SHMs is also an SHM, and the resultant displacement x is given by the formula x is equal to r sin omega t plus delta, where r is the resultant displacement and delta is the resultant phase difference between the displacements. The equation can be solved for r and delta, and you can get the formulae for resultant displacement r as under root a1 square plus a2 square plus 2a1 a2 cos alpha 1 minus alpha 2 and delta as tan inverse a1 sin alpha 1 plus a2 sin alpha 2 divided by a1 cos alpha 1 plus a2 cos alpha 2. Simple pendulum. An ideal simple pendulum is a heavy particle suspended by a weightless, inextensible string to a rigid support. Practically, we cannot get a single particle of large weight as well as a weightless string. Hence, a practical simple pendulum consists of a solid metal sphere of large weight, which is called as bob, suspended to a rigid support by a lightweight inextensible string. The figure shows a practical simple pendulum suspended to a rigid support at O with a lightweight inextensible string. In the mean position A, the line passing through the CG, that is center of gravity of the bob, is along the string. This is the mean position. Hence, the distance between the point of suspension O and the center of gravity of the bob is called length of the simple pendulum L. When the bob is displaced through very small angle theta and released, it moves to and fro along the circular path AB and then BC and then CA. At any position, say extreme position B, two forces act on the bob. The first one is obviously weight of the bob mg acting vertically downwards, and the second force is tension T in the string. Weight can be resolved into two components, mg cos theta along the string and mg sin theta perpendicular to the string or tangential to arc AB. Tension T in the string balances the component mg cos theta. So the only unbalanced force causing the oscillations is mg sin theta. Comparing this force with the condition of SHM, we get that acceleration is directly proportional to minus x, which is the displacement of the bob from the mean position. From the formula for period as 2 pi upon under root acceleration per unit displacement, we get the formula for period of a simple pendulum as 2 pi under root L upon G, where L is length of the pendulum and G is the acceleration due to gravity at that place. From the formula of period, we can write three laws of simple pendulum. The first one, period of simple pendulum is directly proportional to square root of length L of the pendulum, that is T proportional to under root L. Second one, period of simple pendulum is inversely proportional to the square root of acceleration due to gravity at that place, that is T proportional to 1 upon under root G. And remember, there is no mention of mass of the bob or mass of the pendulum, and from that we get the third law as period of simple pendulum is independent of mass of the bob. In case of pendulum, the pendulum having a period of 2 seconds is very important. It is called seconds pendulum. It is a simple pendulum having period of 2 seconds, or it is a simple pendulum which crosses the mean position after every 1 second. Substituting T is equal to 2 seconds in the formula for period of simple pendulum, we get the length of simple pendulum as G upon pi square. Hence, by knowing acceleration due to gravity at any place, we can calculate the length of seconds pendulum. If we prepare a pendulum of this length, it will cross the mean position after every 1 second, which can be used for measurement of time. Up till now, we have studied linear SHM. Let us study angular SHM now. Angular SHM is a type of angular periodic motion in which torque or angular acceleration is always directed towards the mean position and ease of the magnitude directly proportional to the angular displacement of the body from the mean position. Thus, torque tau causing angular displacement theta is proportional to it and directed opposite to it. Hence, tau is proportional to minus theta, or tau is equal to minus mu theta. Mu is called torsional constant or torque per unit twist. Its unit is Newton meter per radian. The differential equation for angular SHM can be written as I d square theta by dt square plus mu theta is equal to 0. I is the moment of inertia of the body in angular SHM. Theta is the angular displacement from the mean position. So, d square theta by dt square is the angular acceleration. The best example of angular SHM is a bar magnet suspended freely in a uniform magnetic field deflected from its mean position. The figure shows a bar magnet of pole strength M and magnetic length 2L. Therefore, magnetic dipole moment of the magnet, that is capital M, is 2mL. It is suspended freely in a uniform magnetic field of strength B. Forces MB act on both the fictitious poles north and south in opposite directions along the same line. Hence, no resultant force acts on the magnet and the magnet remains steady with its axis parallel to the direction of B. When the magnet is rotated through small angle theta and released, a couple acts on it which tends to bring the magnet to its original position or the mean position. But due to inertia of the magnet, it crosses the mean position and gets deflected on the other side. Once again, the torque tries to bring it to the mean position. As a result, the magnet moves along a circular path to and fro about the mean position. This is the angular SHM of the magnet. The period of this SHM can be calculated with the formula T is equal to 2 pi under root I upon mb, where I is the moment of inertia of the magnet, capital M is the magnetic dipole moment of the magnet, which is 2 ml, and B is the magnetic induction. For a bar magnet, the moment of inertia I is given as I is equal to m upon 12 into bracket L square plus B square, where L is length of the magnet and B is breadth of the magnet. Thus, we can calculate the period of oscillation of a magnet suspended in a uniform magnetic field when rotated through very small angle theta.